Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on Java Native Interface and look at Chapter 2 of Oracle's official documentation on Java Native Interface. So Chapter 2 is about design overview of the Jni, and it starts with Jni interface functions and pointers, compiling, loading, and linking native methods. We've seen how to do it. Again, to recap, we create the header files that we need to include in our C++ project using java h-jni or java c-h, and then we create the C++ files, and the C++ project include those header files in our CPP files and then compile as a dynamic library. On Windows the extension is .dll, on Mac OS it's .dylib, and on Linux it's .so. all right, and then we use system.load library to load the dynamic libraries basically in Java at runtime. So the loading of the dynamic libraries happens at runtime, not compile time. So resolving native method names, native method arguments, and then referencing Java objects, global and local references, implementing local references. These two are not something that we typically use, so this is more like a rarely used topic, local and global references. Accessing Java objects, we have discussed these in depth, so like fields, for example, accessing fields in C++, and we said that the mechanism is exactly like Java Reflection API. That's because we need to access the information from the meta space, and all the information of the classes are stored in meta space, the metadata, and in Java we get them with the class object, and in C++ we ask JVM to find the class on the class path, and then that returns a JClass handler to us in C++. Java exceptions, and again we've looked at these in depth. So exceptions, Java exceptions in C++, exceptions and error codes, asynchronous exceptions. Again, this is more about multi-threading, which is again not a topic that we usually use. It's a rarely used topic. Exception handling. So exception handling, we said that there are 4 functions in Jni that we can use to handle the exceptions. There are 2 functions in Jni that we can use to throw exceptions throw Java exceptions in C++. So we can throw a new exception which takes a const pointer, a string, C string, or throw new, or no, actually the throw new takes a C style string, const pointer, and throws a new exception. Throw just throws a J exception. So if we have J throwable, so if we have a J throwable handle, we can just use JVM throw and throw that object again. So exception occurred gives us a J throwable handle on the exception that was occurred. Exception described just prints the stack trace to the console. It doesn't do anything else. Exception clear tells JVM that we are clearing the exception, so it means we are handling the exception. Exception check checks the stack trace if any exception has been occurred, so it returns a boolean or JBoolean. So we can use exception check to see if any exception has been occurred, and then we can decide to handle it or not, or throw it again. All right, so the last topic in section 2 or chapter 2 is Jni interface functions and pointers, and again we have looked at these in different points in our lectures, and we will look at them again. So let's go inside design overview. This chapter focuses on major design issues in Jni. Most design issues in this section are related to native methods. The design of the Invocation Api is covered in chapter 5. And again, Invocation Api is basically how we can invoke or start a Java virtual machine within the C++ code. That's the normal use case is when we want to embed Java in our C++ project. So we can use Jni to embed a JVM or start running a JVM with some initial arguments from within the native code, C++ code. Again, that's a feature that we don't normally use when we develop Jni applications. So this chapter covers the following topics: Jni interface functions and pointers, compiling, referencing Java objects, accessing Java objects, and then Java exceptions. So Jni interface functions and pointers. Native code accesses Java VM features by calling Jni functions. Jni functions are available through an interface pointer. So it's the JVM pointer or Jni inv pointer that we have always used. I always call it basically JVM. So interface pointer, if I go to this slide that we early on looked at the header file that the Java Edge creates, and we saw that the first argument to native calls is Jni environment pointer, and this is the interface pointer. An interface pointer is a pointer to a pointer. This pointer points to an array of pointers, each of which points to an interface function. Every interface function is at a predefined offset inside the array. The following figure, interface pointer, illustrates the organization of an interface pointer. So Jni interface pointer points to a pointer, right? And per thread Jni data structure, and then array of pointers to Jni functions, right? So these are pointers to Jni functions. Description of it. Okay, so the Jni interface is organized like a C++ virtual function table or a COM interface. The advantage of using an interface table rather than hardwired functions interface is that the Jni namespace becomes separate from the native code. A VM can easily provide multiple versions of Jni function tables. For example, the VM may support 2 Jni function tables. One performs thorough illegal argument checks and is suitable for debugging. The other performs the minimal amount of checking required by the Jni specification and is therefore more efficient. The Jni interface pointer is only valid in the current thread. So that's one thing that we need to keep in mind, right? A native method therefore must not pass the interface pointer from one thread to another. A VM implementing the Jni may allocate and store thread local data in the area pointed by the Jni interface pointer. So again, keep in mind that the Jni environment pointer is only valid in the current thread. And in my lectures, I didn't go into how we can do Jni application development when we are dealing with a multi-threaded Java application. That gets complicated to some extent, but for now we don't need to worry about that. Native methods receive the Jni interface pointer as an argument, and it's the first argument, Jni environment pointer. And if we generate the header file using the Java Edge, this prototype is already created for us, and the Jni environment pointer is the first argument. All right. And then the second argument is equivalent to this pointer if it's a non-static method in Java. If it's a static method in Java, the C++ binding basically handles the static method as a J class. So the second parameter to the header, the prototype of the native call, is J class instead of J object when we deal with static methods in Java, or basically we try to bind a static method in Java to a C++ native function, right? And then the other thing is that we said that even if we use the Jni Unload and then do basically manual binding, when the Jni basically loads the dynamic library, instead of going through the Java Edge and creating the prototypes, we can do eager binding of Java methods to C++ functions. So let me see if I can find it. Eager binding or eager linking. And when we discuss the power of register native function, so JVM or Jni environment pointer has this very interesting function called register natives. You pass it a J class that has the meta information, and then a Jni native method pointer, which can be one single Jni native method, or it can be an array of Jni native method, and a JInt, which tells the JVM how many methods we are eagerly linking or binding, right? Eager linking or eager binding. And when we do this, we don't use Java Edge, we don't create any header files, right? However, Even in this case, when we define this function pointer that tells JVM this method in this J class or in this Java class binds to which C++ function, right? This native pointer or function pointer must take the Jni environment pointer as its first argument and then a J object or J class as the second argument. So we cannot, as we saw in this lecture when we talked about the register natives, we cannot have this function pointer that points to any arbitrary C or C++ function. It has to take the Jni environment pointer as the first argument and then J object or J class as the second argument. That's one of the limitations here. All right. Native methods receive the Jni interface pointer, the Jni interface pointer as an argument. The VM is guaranteed to pass the same interface pointer to a native method when it makes multiple calls to the native method from the same Java thread, right? So JVM always per thread applications, the Jni environment pointer as I call it, the JVM. As you can see in the next slide here, Jni environment pointer, I call it JVM. And it's guaranteed to be the same when VM calls a method, native method multiple times. However, a native method can be called from different Java threads and therefore may receive different Jni interface pointers. And again, in my lectures, we didn't really discuss multi-threaded applications and how to handle the Jni calls. But what you need to know here is that that Jni environment pointer that goes into the first argument of the native method, it's guaranteed to be the same for a thread per thread. But when we do multi-threading and a native method called from different threads, this JVM might change, might be different, right? Native methods, okay, all right. Compiling, loading, and linking native methods, and we have talked about this many times. Since the Java VM is multi-threaded, native libraries should also be compiled and linked with multi-thread aware native compilers. For example, the -empty flag should be used for C++ code compiled with the Sun Studio compiler. For code compiled with the GNU GCC compiler, the flags -d reiterant or -d POSIX C source should be used. And again, this is something that we didn't really discuss in my lectures, but if you are doing multi-threaded applications, you should be aware of this, right? For more information, please refer to the native compiler documentation. So for GNU GCC, -d reiterant or -d POSIX C source. Native methods are loaded with the system.load library. And we also have another one. So system.load library is a typical use case. And we said that on Mac OS or Linux, when we compile a C++ to create a dynamic library, the lib gets added to the beginning, gets added as a prefix. But when we use system.load library, we have to drop that lib from the beginning in Mac OS and Linux. In Windows, we should not drop the lib from the beginning. So if there is a lib at the beginning of the name of the dynamic library is Windows that has the extension of DLL, we shouldn't drop it. So only in Windows. In macOS and Linux, if there is a lib at the beginning of the name of the dynamic library, we have to drop it when we use system.load library. Now there is another version that system.load instead of system.load library is just system.load. System.load takes the absolute path to the library file, the DLL or dilib.so, which means it takes the full path, including the full name of the library, right? System.load library searches inside the path that is specified by -d java.library.path. All right, -d java.library.path includes all the directories that may have dynamic libraries for our applications. And again, on Windows, the path separator is semicolon. On macOS and Linux, the path separator is colon, right? So if we want to specify multiple directories that contain dynamic libraries, we separate them with colon in macOS and Linux. In Windows, we separate them with semicolon, all right? So this is again something that to have in mind. In the following example, the class initialization method loads a platform-specific native library in which the native method f is defined. So package, this is our Java code, class, native, double f, int I, string s, and so this is our native method. Its implementation is inside the native code, inside the dynamic library, and we typically load the dynamic libraries using a static initializer. That's because basically what happens, again, to reiterate, we have to tell JVM or Java where the library is, and we use that with the -d java library.path, and then we have to tell JVM or Java when to load it into the memory. And obviously we have to load the dynamic library before we call the native method. And it's because a class might have multiple native methods and the user might call any of them at any time, it's best to load the dynamic library when the class is loaded into the memory by the class loader. And when does that happen? It happens when any static when the class is instantiated or any static method is accessed, any static field or method is accessed, right? Now, obviously, any code that goes inside the static initializer gets executed after the class is loaded into the memory. So that's the optimal, or that's the desired place to load the dynamic library, because that guarantees that as soon as the class is loaded into the memory, even before it's being instantiated, then the dynamic library is loaded and the class is ready to go. And another good reason why we need to load the dynamic library in the static initializer is that a native method can be static. So if it's a static native method, we don't even need to instantiate the Java object, right? We can directly access it via the class, because static methods are class level methods. And again, when we access a static method, the class gets loaded into the memory, and we want the dynamic library to be loaded before the static method is executed, right? Otherwise, we get an unsatisfied link error. That's why we put the dynamic library inside the static initializer. The argument to system.load library is a library name chosen arbitrarily by the programmer. I mean, it's the name of the dynamic library. And on macOS and Linux, we have to drop the lib from the beginning, and we always need to drop the extension, right? Even on Windows, we drop the .dll. The system follows a standard but platform-specific approach to convert the library name to a native library name. For example, a Solaris system converts a name package_class to lib package_class.so. And again, this is the standard on all Unix-based systems like macOS and Linux. Lib gets added to the beginning, and .so or .dylib gets added as an extension, while a Win2 system converts the package class to package class.dll. So on Windows, the convention is that the lib doesn't get added to the beginning, or Windows doesn't recognize it, or the JVM doesn't recognize it as something that has to be dropped. So if in Windows we just add the .dll. The programmer may use a single library to store all the native methods needed by any number of classes, as long as these classes are to be loaded with the same class loader. So that's another thing. So if you choose, basically the class loader, if all the classes that have native methods have the same class loader, which is typically the case when we write our own custom classes, right? Write our own classes that have native methods. They all get loaded by the basically system class loader that searches the class path, right? The bootstrap class loader, and then the extension class loader, and then we have the system class loader that searches the class path. The VM internally maintains a list of loaded native libraries for each class loader. Vendors should choose native library names that minimize the chance of name clashes. A native library may be statically linked with the VM. All right, so far we've seen that we dynamically load the library. That's why it's called dynamic linked library. It can get loaded at runtime, not included at the compile time. But native library may be statically linked with the VM. The manner in which the library and VM image are combined is implementation dependent. So when you build your Java binaries, you can statically link other dynamic libraries if you want to. And I mean, most of us, we don't build the Java ourselves. We just download the binaries from OpenJDK or Oracle's website, or adopt Java or whatever, adopt JDK. That's why we have the binaries which have been already compiled, so we cannot do static linking with those binaries. A system.load library or equivalent API must succeed for this library to be considered loaded. Oh, by the way, we cannot use a system.load library to load static libraries. We can only load dynamic libraries. A library L whose image has been combined with a VM is defined as statically linked if and only if the library exports a function called Jni Unload L. All right. We saw that the Jni Unload gets executed when the dynamic library is loaded into the memory. And then if we are doing a static linking with the VM image, with the VM binary, we have to include Jni _unload _L. If a statically linked library L exports a function called Jni Unload L and a function called Jni Unload, the Jni Unload function will be ignored. So Jni Unload is basically an indicator of the dynamic library. When the dynamic library gets loaded into the memory, Jni Unload gets executed. And let me bring up the lecture that we had, Jni Unload. Jni Unload, this is the load handler. Jni Unload, it takes a Java VM pointer argument and a void pointer reserved. And we can get a handle to JVM, to the Jni environment pointer from this Java VM pointer argument. So we use the VM get environment that gives us the environment or the JVM that we need to work with. We pass in the address of JVM, this Jni environment pointer, and the version of the JDK that we want to work with. And this basically returns the JVM. Basically, we are passing by reference, so JVM gets initialized inside this function get environment. And again, when we are building or compiling the Java itself to create the binary of the JVM, we can do a static linking. And in that case, the Jni Unload will be ignored and the Jni Unload L will be used. If a library L is statically linked, then upon the first invocation of system.load library L or equivalent API, a Jni Unload L function will be invoked with the same arguments and expected return values as specified for the Jni Unload function. And again, Jni Unload L for static linking, Jni Unload for dynamic linking. And the use case here is that as soon as the dynamic library is loaded by the JVM, the Jni Unload is called. So we can do some initialization. A library L that is statically linked with will prohibit a library of the same name from being loaded dynamically. Obviously, that's an obvious thing. When the class loader containing a statically linked native library L is garbage collected, the VM will invoke the Jni Unload function of the library if such a function is exported. And the same for dynamic library. So just like Jni Unload, we have also Jni Unload when the dynamic library is when the class is garbage collected and the dynamic library is unloaded. The programmer can also call the Jni function register natives, which we discussed in very details. To register the native methods associated with the class, the register natives function is particularly useful when statically linked functions, with statically linked functions. And again, as Java programmers, we don't do a static linking, we do dynamic linking because we just download the binaries of the Java JVM, so we cannot statically link any library. Resolving the native methods. Dynamic linkers resolve entries based on their names. And again, in order to have a unique name, Java uses Java H, or the header files that are generated by Java H or Java C-H. They follow a particular rule for naming. Dynamic linkers resolve entries based on their names. A native method name is concatenated from the following components: the prefix Java underscore, and Java is capital. This shows that this C++ function, the prototype of this function, is a binding to a Java method. A mangled fully qualified class name. Mangled means just all the basically package hierarchies and then separated by underscore. An underscore separator for every package and every class name and method name, a mangled method name at the end. For overloaded native methods, 2 underscores followed by the mangled argument signature. And this is something we discuss in depth. Signature are overloading, and we said that Java underscore package name underscore class name underscore method name is the standard, but then Java allows basically method overloading. And if there are 2 native methods that overload each other, then in C++ we have to differentiate their signatures somehow. And the way the Java Edge or Java C-Edge resolves this naming to get a unique name for the functions is that it adds 2 underscores and then method parameter signature. Remember, method parameter signature. Return type of a function doesn't play any role in the overloading, right? So 2 functions overload each other if the name are the same, but the parameters are different. It doesn't matter what the return type of the 2 functions or the 2 methods are, right? Return type doesn't play any role in the definition of method overloading. Doesn't matter if one of them is static or not, doesn't matter if one of them is native or not. But if we have 2 native methods that overload each other, then we have to have a unique name for each of them in C++ for the bindings, right? For the function prototypes. That's why we have to differentiate them by method parameter signature, and we use underscore underscore. For overloaded native methods, 2 underscores followed by the mangled argument signature. The VM checks for a method name match for method that reside in the native library. The VM looks first for the short name, that is the name without the argument signature. It then looks for the long name, which is the name with the argument signature, this method parameter signature. Programmers need to use the long name only when a native method is overloaded with another native method, right? And we some different examples that if I have a native method but then overloaded with a non-native method, the Java Edge didn't add this underscore underscore method parameter signature because we only have one native method, right? So it doesn't matter. So this whole business of underscore underscore parameter signature is for the case when we have more than one native method that overload each other. And the reason is that we need to, the functions must have unique names in C++, right? That's why we have to differentiate somehow. However, this is not a problem if the native method okay, so programmers need to use the long name only when a native method is overloaded with another native method. However, this is not a problem if the native method has the same name as a non-native method, which means if a native method is overloaded with a non-native method, we don't add this underscore underscore parameter signature. A non-native Java method does not reside in the native library, obviously. If in the following example, the native method G does not have to be linked using the long name because the other method G is not a native method and thus is not in the native library. Okay, and I have an example here. For example, so we said that overloading native with non-native methods, no need to add method param signature to the native function. To the prototype that binds to this native method. That's just because we only have one function that binds to this Java method, so there is no need to differentiate it with another function, right? So CLS1 int G, int I, native int G, double D. And again, it doesn't matter if the return type is the same or not, only the name of the method and the parameter signature are the definition of overloading. So I have the same name for the method but different parameters, so this is a valid overload. I can overload a native method with a non-native method regardless of what the return type is. I can overload a method with a static method even, that's fine. We adopted a simple name mangling scheme to ensure that all Unicode characters translate into valid C names. And again, C in the source code, it only allows UTF-8, which is backward compatible with ASCII. However, Java in source code allows UTF-16. So then if we use some weird character that is not inside UTF-8 in our Java source code in method, then they had to handle it somehow in C++ or C. And we have already seen a very famous example, which was the $sign. If you recall, when we talk about the anonymous classes, we saw that or inner classes, we saw that the $sign was replaced by _0 and then 2 zeros and 24, and this was like a mystery, but I explained where this $sign coming from, basically where this 00024 is coming from, and it's explained here. We use underscore character as the substitute for the slash, forward slash, and the forward slash is basically class path separator, right? So in the name mangling, we saw that the signature is Java underscore the class path description underscore method name, right? And this class path is basically is package slash another package slash the class name, and the slash is replaced by underscore. And again, we discussed this in more details here. So a slash is replaced by underscore in fully qualified class name. The fully qualified class name, again, in Java source code, the separator is dot. But as soon as we go into the class file, dot class file, inside the JVM, it's a slash. Inside the JVM, there is no dot. It's always a slash. I don't know why, but it's not dot anymore. So the class path separator is actually forward slash, not dot, inside the JVM. And when we are doing Jni in C++, we talk to the JVM. There is no such thing as Java source code anymore. And inside the JVM, everything is forward slash. So we replace the underscore. We replace forward slash with underscore, which is for the fully qualified name, class name, and then underscore method name. Since a name or type descriptor never begins with a number, we can use _0 _9 for escape sequences, as the following table illustrates. So this is where that weird, basically, this is where it explains why that we saw this replacement. For example, semicolon was replaced by _2. A square bracket for arrays was replaced by _3. Underscore itself in the Java, if we have like underscore in the package name or class name or method name, it replaced by _1. And this is, as you can see, it's a general rule that the developers of Jni implemented. And these _1, _0, _1, _2, all the way to _9 are used whenever we want to implement some escape character in our C++ function prototype that binds to a Java method, right? So these are, we can use _0 to _9 for escape sequences. We have seen _1. _1 is just underscore itself when we have an underscore in the package name or class name or method name, right? Or method parameter signature, which is basically either the primitive, which don't have any underscore, or classes, and classes are replaced by fully qualified name, so underscore is automatically there. So underscore is replaced by _1. Semicolon is replaced by _2, and semicolon was in the signature of objects, right? And objects start with L and then fully qualified class path and then semicolon, and then we have to, when we have these method parameter signatures and we want to add them in for the overloaded native methods, we have to add the fully qualified name. And then when we do that, objects start with L, end with semicolon, and then semicolon is replaced by _2. _C is for arrays, right? The character a square bracket in signature, so a square bracket replaced by _3. So what is this _0 and then XXXX? This is exactly where we discussed the $sign. So $sign, let's say if I have an inner class, its fully qualified name, or basically its class path is the class path of the outer class, and then $sign, and then the inner class for nested classes. For anonymous classes, it's $sign _1, 2, etc. And we said that the inner classes or anonymous classes can have native methods. And then, for example, for an inner class, the signature $x, we have to, if we are overloading that, or basically, even if we're not overloading it, this $sign is part of the fully qualified name. Therefore, it has to be in the C++. C++ functions name cannot have $, so we have to replace it with something else, and they're using the UTF description with the escape sequence of _0, right? So when I have a $, which is a non-standard character, what we do, we escape it with the _0 and the 2-byte description UTF-16. It's a Unicode character XXXX, and we saw that basically the Unicode UTF-16 description of $ is 2 zeros for the first byte and 24 for the second byte. And then _0 is added as the escape sequence. So we are escaping it. Any Unicode character XXXX, note that lowercase is used to represent non-ASCII Unicode character. For example, _0 ABCD as opposed to _0 ABCD. So it always uses lower characters. In terms of the $, they don't have ABCD. I mean, all the bytes, basically each 4-bit is numeric, non-character. So there's no problem with the lowercase. But it says that they always use lowercase, not the uppercase, which is fine. It doesn't really matter for when we represent. Remember that this is the hex representation, 2-byte Unicode UTF-16. Both the native methods and the interface APIs follow the standard library calling convention on a given platform. For example, Unix system use the C calling convention, while Win32 systems use __std call. Native method arguments. The Jni interface pointer is the first argument to the native method. We've seen this many times. So Jni environment pointer or interface pointer is always the first argument to the native method. The Jni interface pointer is of type Jni environment. The second argument differs depending on whether the native method is static or non-static. So again, this is something that we have discussed many times, that the first argument is always Jni environment pointer. The second argument depends on whether the method that binds to the C++ function is a static method or a non-static method. The second argument to a non-static native method is a reference to the object. It's like a this pointer in Java. So we get a JObject reference. The second argument to a static native method is a JClass, is a reference to a Java class. The remaining arguments correspond to the regular Java method arguments. The native method call passes its result back to the calling routine via the return value. Look at chapter 3, it describes the mapping between Java and C types. And we have looked at the mappings before, and we will look at it soon. The following code example illustrates using a C function to implement the native method f. The native method f is declared as follows. Again, it all talks about the C, but we know that we all do C++, right? That's why in the header file the extern C line is added, because this whole Jni business was designed for C. C++ luckily is backward compatible with C, but then C++ allows basically namespaces. Therefore, it does some name mangling in the name of the functions, but Java doesn't understand that. This is the strict rule that the JVM follows when it looks up the name of the the functions that bind to the Java method. So if that's why these functions always have to be in the global scope. There shouldn't be any namespace inside any namespace, otherwise the JVM cannot find them. But then if we are compiling with C++, we have to tell the C++ compiler to not do any name mangling on these Java binding functions. That's why we use the extern C to tell the C++ compiler, hey, don't do any name mangling. Exactly put the name of these functions exactly the same way without any name mangling, without changing it in the binary file in the dynamic library. That's why this extern C is there. We want to make sure that the JVM can find exact name that corresponds to this declaration. So we have a native double F int I string, the C function with the long mangled name. So Java underscore package name, class name. So fully qualified name, package under package / class, and then / is replaced by underscore. That's the fully qualified name of the class. And then underscore method, and then that's it, because if we are not overloading it, we don't need to specify the parameter signature. But here it is providing the parameter signature __ I. Actually, this should be 2 underscores. I for the first parameter integer and a string s. L Java lang string semicolon _2 is semicolon, and L semicolon signifies a Java object. Implements native method f. So it returns a J double. We know that a J double directly maps to double Java, okay. And then the first parameter is Jni environment pointer. I call it JVM, and then this is not a static method. It's a regular non-static method. So the second parameter is the J object, and then J int maps to int, and J string is a handler for the Java string, right? Obtain a C copy of the Java string. We know that the C++ strings or C style strings are not compatible with Java because of the whole UTF-16 versus UTF-8 business. That's why we use JVM and get a string UTF-chars. We pass it and again, this is a C style calling. We don't use this in C++. Later on, they actually added the C++ support to the JNI. That's why it adds this extern C. And instead of doing this and passing the environment again, we just basically say JVM get a string UTF-chars. We pass the J string, and is copy is the second parameter. And we already looked at whether or not JVM, the Oracle's JVM at least, creates a copy or not. It's left to the implementation, but most I guess almost all VMs give you a copy. So internally they create a copy, and this const_char pointer points to a copy of the string. That's why when we create this pointer, it's a copy gets generated on the native heap, and then we have to clean it up before returning. That's why we release the string. And again, this style of calling, passing the environment pointer here, it's for C functions. In C++, if I look at the top discussion that we had on the strings, working with strings, Java is UTF-16, L Java /lang string semicolon, and then char pointer is a character array. Std string is added in C++, and if we want to get the const_char pointer or the C style string from the std string, C++ string, we use the method C_str to give us the C string, right? And then we said that J string environment or JVM new string UTF. This is how we create new Java string, and const_char pointer string environment get a string UTF-chars. We passing a J string, right? And then the second parameter is copy. It's a JBoolean pointer, and we can check. We can pass a reference to a JBoolean, and when this function returns, we can check whether this is copy is true or false, or 0 is and non-zero. That tells us if JVM is giving us a pointer to the actual string, or is giving us a pointer to a copy of that string. And we say that almost all the time it's a copy, because strings are immutable, so JVM doesn't give us direct pointer. But we saw that in order to get the direct access, we have to use the critical access. So again, this environment, dereferencing it and passing it as the first parameter, this is the old style or C style. In C++, we don't do that, or basically they added the C++ support so that the code becomes more readable. Now we are done with the string, and this was a const_char pointer, a copy that was created on the native heap, and so we have to delete it. So JVM doesn't do any resource management for us, because it's the job of the garbage collector, not the JVM. And in C++, we don't, the garbage collector is just not doing anything. Note that we always manipulate Java objects using the interface pointer, this JVM or environment. Using C++, you can write a slightly cleaner version of the code as shown in the following code example. Yeah, so environment get a string UTF-chars, S is our J string, and then is copy, we pass it. Remember, this takes a JBoolean pointer, and 0 is just a null pointer. So we just pass a null pointer here because we don't care, and we don't, or actually we don't want to check because we don't care if it's a copy or not. If we want to check, we have to, before this line, we have to create a JBoolean object and pass it, or JBoolean type. JBoolean is just a primitive C++ type, right? JBoolean is just unsigned char, is a 2-byte unsigned integer, or actually 1 byte. JBoolean is unsigned char, so it's unsigned 1-byte integer. And then when this function returns, if we pass a reference to a JBoolean, then we can check if it's 0 or non-zero. But here we're just passing null pointer. Obviously in C++, instead of using null or 0, it's better to use the null pointer keyword. And then environment release a string UTF chars, right? And we said that the garbage collector doesn't clean native heap. So when we are in C++, these things, this const pointer gets generated on the native heap, and the garbage collector only cleans up the basically the Java heap, not the native heap, right? Another thing is that as a general rule, we said that whenever we use a Jni function that returns a pointer to us, we have to also manage it ourselves manually. And the way we manage it is we use the function release. So if you have get a string UTF chars, there is another function release a string UTF chars. If it's like a get array or whatever, get object, if anything that gives us a raw pointer, then we have to also, and there is another function that it starts with release that we have to call it when we want to deallocate and delete it. With C++, the extra level of indirection and the interface pointer argument disappear from the source code. However, the underlying mechanism is exactly the same as C. In C++, Jni functions are defined as inline member functions that expand to their C counterpart. Okay, referencing Java objects. Primitive types such as integers, characters, and so on are copied between and Java native code. Obviously, this is very easy to do. Arbitrary Java objects, on the other hand, are passed by reference, right? Because they're already inside the Java heap. So all we have to do in C++ or C is to give the pointer to them. The VM must keep track of all objects that have been passed to native code so that these objects are not freed by the garbage collector, obviously. The native code in turn must have a way to inform the VM that it no longer needs the objects. In addition, the garbage collector must be able to move an object referred by the native code. The garbage collector must be able to move an object referred to by the native code. Global and local references, and again, this is not something that we typically use, but I'm going to quickly go through it. The Jni divides object references used by the native code into two categories: local and global references. Local references are valid for the duration of a native method call and are automatically freed after the native method returns. Global references remain valid until they are explicitly freed. Objects are passed to native method as local references. All Java objects returned by Jni functions are local references. The Jni allows the programmer to create global references from local references. Jni functions that expect Java objects accept both global and local references. A native method may return a local or global reference to the VM as its result. In most cases, the programmer should rely on the VM to free all local references after the native method returns. However, there are times, and that's the reason that in my lectures I didn't really emphasize on this fact, because VM could handle it unless there are two cases when we have to manually interfere with what VM is doing. There are times when the programmer should explicitly free a local reference. Consider, for example, the following situations. A native method accesses a large Java object, thereby creating a local reference to the Java object. The native method then performs additional computation before returning to the caller. The local reference to the large Java object will prevent the object from being garbage collected, right? So even if we have a local reference in the C++ code, the garbage collector in Java, it's not allowed to claim it, even if the object is no longer used in the remainder of the computation. A native method creates a large number of local references. So if we have a very large for loop inside a C++ code and it just creates local references of an object, it creates lots of J objects, for example. A native method creates a large number of local references, although not all of them are used at the same time. since the VM needs a certain amount of space to keep track of local references. So basically VM has an initial counter of what is the maximum number of local references that it allows to be created, and we can override that parameter of the VM. Creating too many local references may cause the system to run out of memory. For example, a native method loops through a large array of objects. So array of objects, that's one of the cases when we really need to make sure that we're not going out of the bounds of that number of local references and that the VM allows us to do. We looked at the basically array of objects, right? J object array, new object array, set double array region, set object array region. But here we didn't really discuss this concept of local references and how to manually free them or delete them, because typically we don't really go overboard with the limitation, with the limit that the VM has. For example, a native method loops through a large array of objects, retrieves the elements as local references, and operates on one element at each iteration. After each iteration, the programmer no longer needs the local reference to the array element, and the programmer can just delete them. The Jni allows the programmer to manually delete local references at any point within a native method. To ensure that programmers can manually free local references, Jni functions are not allowed to create extra local references, except for references they return as the result. Local references are only valid in the thread in which they are created. And again, going back to multi-threading, the native code must not pass local references from one thread to another. Okay, so I guess that's it for this lecture. Please stay tuned and I'll see you in the next one.